Hello. The topic of this lecture is the presentation of Markov chain Monte Carlo simulation. This is a quite complex and advanced method to draw samples from probability density functions that are very difficult otherwise to sample. So the inverse cumulative distribution method wouldn't work or would be impractical in problems, in some problems. And the solution, or one of the solutions, is to use Markov chain Monte Carlo simulation. An example is if you want to draw samples from the conditional probability density function of one or more random variables, given that an event has occurred. For example, that the stress in a beam exceeds a minimum allowable level, okay, or a minimum level. So this is one type of probability density function that you cannot sample from using the inverse cumulative distribution function. The reason is maybe the failure domain is very small. So if you try to sample from the failure domain that you cannot define well, then you cannot do it. It's tricky. Okay? So this is the use of this method. Okay, so how does it work? You start from one state, let's say x1. This is the initial state. Then you make a step, you move to another state, okay? Now, at this state, you do a test. That test tells you whether to stay in this state or return back to the original state, okay? So you do a test, and either you proceed to the next state or you go back. If you go back, this is considered the original state becomes also the new state. So x1, if you go back, will become state x2. So you will have two states that coincide. Okay. Then you do the same thing. If you try to move again to x2 or another position, either you will move or you return. So suppose that you move to this position. Once you move to this position, you do a trial step, you go to another state, and then you make a test. And if you pass the test, you make this x3, the new state. Otherwise, you return and make x2, the state x3. So you have two states that coincide. And you repeat this process, and the samples that you end up with in the end are from this distribution, from the target distribution. Okay? So this is the method. Now let's do a flow chart of this method. So sampling from a PDF. F, X, X, okay. This is a random vector. That means a bunch of random variables, x1, x2, etc. And these are the values, okay. So this is a random vector. And these are the random variables. I'm sorry, the values of the random variables. Values of random variables. Okay, so these are numbers, these are names of variables. Okay, the first step is to select an initial state. let's say x1. And the probability density function should be non-zero at x1. So such that the probability density function of x evaluated at x1 is non-zero, okay? So there is a non-zero probability to be in this state x1, the original state. Then you draw a candidate state, x2. So draw candidate state x2, and you do that from a transition probability density function ADF fx2 given x1 So you just take a step. You have not adopted yet x2 as the new state, okay? You're going to do a test to decide whether to adopt it. So the next step is make x2 the next state with probability the ratio of the two densities if this ratio is less than or equal to 1. If this ratio is less than or equal, greater than, less than or equal to 1. Okay. So, the higher the probability density function of the next state, the more likely is to stay in that state, okay? So this is what you do. If the ratio, if this ratio is greater than 1, this is the case where it is less than 1. If this ratio is less than, greater than 1, then make x2 the next state with second. And make x2 the next state. Okay. Now, if the ratio is less than 1, make x1 the next state. That means to return to x1. With probability one minus this ratio. Okay, so this is the step where you do a test to decide whether to move to x2 or to return to x1. Okay? So again, when you go to x2, you check the likelihood ratio. You check the ratio of the density of x2 to the density of x1. And if this ratio is less than 1, then you accept this state with probability equal to the ratio. So the higher the likelihood of x2 compared to x1, the more likely it is to move to the new state. If it is greater than 1, this ratio, which can happen because these are probability density functions, and the ratio can be greater than 1, then you move to the new state for certain. Okay? Any questions? So if you follow this process, you create sample values that are from the target probability density function. Okay? And this probability density function may not have a closed form expression. We're not talking about a normal or a Weibull. Here we're talking about distributions like the conditional distribution of a variable, given that some event like a failure has occurred. Okay? So these are complex probability distributions. And you repeat this process until I is equal to n. Repeat this process until I becomes equal to a maximum value. Okay? So this is the procedure. And again, you sample from a very difficult distribution that otherwise you wouldn't be able to sample. Okay, any questions about that? So what do we do with this process? Suppose that you created a sample from this difficult distribution. What do you do with it? What is the benefit? Okay, so let's see. Suppose that you want to calculate the probability of failure, and failure occurs when the displacement of the stress exceeds a very high level, such that the probability of that exceedance is very small, say 10 into the minus 5 or 10 into the minus 6. If you try to do Monte Carlo simulation, that is difficult. Okay, you need a lot of sample values if it is standard Monte Carlo simulation. Sometimes you may not be able to use importance sampling because you cannot guess what is a good sampling distribution. Say you have many random variables, or the failure domain is so small that somehow you cannot, you don't really know what is a good sampling distribution. So this is where this method works well. So let's say that you want your objective is to estimate probability that x exceeds x max. Okay, so this is the system response. And this is the failure limit. And x max is so high that this probability is very small. Okay? So because it's so small, it's difficult to create sample values. So here is what we do. First, we select an intermediate level, and we pretend that that's a failure level. So select intermediate level. let's call it x0, and this is less than x max. Okay? If this is a lower limit than x max, then the failure region is broader, it's bigger, so it's easier to calculate x0, right? So you calculate the probability to exceed x0 using standard Monte Carlo simulation. So calculate probability that x will exceed x0, which is a lower level, so we're talking here about a higher probability, something like, say, 1%, using standard Monte Carlo. Okay? So if this is a higher probability, you need fewer samples to calculate it. Okay? So this can be done. Okay. The next step is to create a sample from the conditional probability of variable x, conditioned upon this event, that x actually exceeds this intermediate limit. Okay? So here is where we use Monte Carlo Markov chain. So perform Markov chain Monte Carlo to sample from this conditional density function, that is the density of x, given that you have already exceeded x0, this limit. Okay? So now, if you use Markov chain Monte Carlo, you will sample in a smaller region, okay, for which we have exceeded this intermediate level. All right. What is the next step? Suppose that you did that. Well, if you have sampled from this conditional distribution, then you can find the probability of failure given that this event has occurred. That means the response is greater than x0. So the next step is to find the conditional probability of failure given that you have exceeded an intermediate level. So find the probability that the response exceeds the maximum given, so this slash means given, that you have already exceeded the limit x0. How do you do this? How do you find this probability? Well, if you have already a sample here, and all these values already exceed, you know that exceed x0, then a subset of these values exceed also x max. So you find the relative frequency of exceeding this limit, given that x is greater than x0. Any questions about this? Okay? So once you have this conditional probability and this unconditional probability, what is the final step? So we want, in the end, to find the probability that x exceeds x max. So how do we do that if we have this probability to exceed an intermediate level x0 and the conditional probability to exceed x max given that we have exceeded this limit? How do we do that? So let's say that the probability that x, I'll put some numbers to make it intuitive, exceeds the limit 30, say that's an intermediate level, and let's say that this is 1%. Okay, we found it from standard Monte Carlo simulation. But what we want to find is the probability that x exceeds the limit, say 180. Okay, this is what we want to find. Now, when we do Markov chain Monte Carlo, we calculate this conditional probability, which means in this case, we calculate the probability that x will exceed 180 given that it exceeded 30. Okay? And let's say that this conditional probability is 10 to the minus 3, 1 per 1,000. Okay, so how do you find the probability that you have exceeded 180, the unconditional probability? It is the product, right? So it is the product of the conditional probability of exceeding 180, given that we exceeded 30, okay, times the probability to exceed 30. So you multiply the two, and you find the unconditional probability. So if out of all the samples that you have generated with Markov chain, let's say 1 per 1,000 exceeds 180, and then you know that this probability is 1 per 100, then you multiply the two, and you find that the probability of failure is 10 to the minus 5, 1 per 100,000. Okay? So, in general, the probability of exceeding this limit is the probability to exceed x0 times the probability to exceed the limit x max, the high limit, which is very rare to exceed, given that you exceeded x0. So this is the final calculation. How do we call this equation? There's a theorem associated with this equation. Well, it involves a conditional probability. So this is like asking you, what color was George Washington's white horse? Okay? So this is the conditional probability theorem. Okay? Conditional probability theorem. And it turns out that it is much easier to calculate these two intermediate probabilities rather than calculating directly the low probability that is 1 per 100,000. Okay? So we take advantage of this method. So the advantage of this method is that it's easier to calculate two intermediate probabilities than that are high rather than one that is very low. So advantage of this method can calculate the probability of this intermediate level and the conditional probability exceeding this intermediate level, of exceeding the maximum limit, given that you exceeded the intermediate limit, more accurately, or with fewer applications, than directly calculating this probability x greater than x max. Okay? So if someone tells you calculate the probability, a probability that we estimate that is in the order of 1%, and another that is in the order of 1 per 1,000, this is the total calculations are much fewer than calculating something that is occurring 1 per 100,000 times. Okay, that's the bottom line. All right, any questions? Now we're going to run a program and solve a problem that involves Markov chain Monte Carlo. Okay, we have a 2-degree of freedom system. There are two masses, M1, capital M, lowercase m, and these are the two natural frequencies. And there is an excitation force which is sinusoidal, with frequency omega e, okay? We had said that this is a system with a dynamic vibration absorber, and this is a good solution to suppress vibration without modifying the original system. So if you have this system and the natural frequency is close to the frequency of excitation and it oscillates a lot, one way to suppress vibration is to attach a second system, and the second system is tuned to the frequency of excitation. So essentially, it takes this system the energy, and theoretically, if you have a perfect tuning, this mass is not going to move at all. Okay. However, we said that the system is sensitive to imperfections. For example, if there is some variation in the mass that you cannot control, then the design may not be effective. And in fact, it can vibrate more than it would without a dynamic vibration absorber. So this is, in a way, if you have a problem like this, you have to consider the variations in the property of the system. For example, the masses, natural frequencies, frequency of excitation, to make sure that the system will not fail. Okay. The equation that you see there is the displacement of the primary system as a function of 4 random variables. These are the ratios of the natural frequencies of the primary system and the excitation And the dynamic vibration absorber and the excitation, these are two ratios. This is the ratio of the two masses, R, and this is the damping ratio. Damping also is important because it affects the vibration level. The higher the damping, the better the suppression. Okay, and we had said last time that if beta 1, which is the ratio of the frequency of excitation to the natural frequency of the primary system, if that is equal to 1, and beta 2 is also equal to 1, this numerator becomes 0, the denominator is still not 0, so the vibration is completely suppressed in theory. Okay? Here we have a plot of the displacement as a function of the two frequencies, the natural frequencies, the frequency of the primary system and the frequency of the absorber. Now, if you have perfect tuning, then you are somewhere here and the vibration is 0. However, if things deviate from the nominal values, the vibration can become very large, something like 40 times the quasi-static response. Okay? Quasi-static means force divided by the stiffness of the original system. So we have to find what happens if you have imperfections in the system. Okay. This is a log that shows the parameter, the random variables. Sorry. Okay, anyway, I guess I cannot control this from this computer. The limit, the intermediate limit is 30, and we have this index function, which is 1. That means failure if x exceeds a maximum level, this limit 30, this is the intermediate limit, otherwise it's 0. Okay, now we have a transition probability density function which gives you the probability to move to another position if you are at an original position. This is the initial state. So the values of the variables of the initial state. And in the initial state, we check and see that the displacement of the system is almost 38, which means that you exceed that limit, the intermediate limit of 30. So this will be your initial point. This point here will be your initial point. And the values correspond to this, okay, to this vector. So the two natural frequencies are 3% higher than the nominal frequency. This is the mass ratio and this is the damping ratio, okay? And first we create a Markov chain with 40,000 steps, okay? So this is the program for Markov chain, and I will not go through it because it's complicated, and I don't think it's a good practice to go through a program in the class. But essentially it puts on this vector all the states, the 40,000 states that it will generate, okay? So we run this program, and then we have, in this vector, we have the variables, beta 1, This is the second variable, beta 2, so you have 40,000 values, 40,000 values here, 40,000 values. This is for the mass ratio, and this is for the damping ratio. Okay, and in the last, we have the displacement. So we have 40,000 displacements, okay, and all of them exceed this limit of 30,000, okay? So what are we going to do with these displacements? We generated 40,000 displacements. All of them are bigger than 30, okay? Then what can you do with this? Well, if you want to find the probability to exceed 100, then you can find the proportion of all these displacements that exceed 100. So this already exceeds 30, so you can find what proportion exceeds 100, or what proportion exceeds 150, okay? So what are these probabilities that you can easily calculate using this information? All these displacements that are above 30. Well, you are sure that they exceed already 30, so if you calculate the frequency of exceeding 100, then you are getting an estimate of the conditional probability of exceeding 100, given that you already exceeded 30. So you can get a lot of conditional probabilities using this vector. And it's not only for one limit, 100, you can use to calculate 150 or 180. Okay, so you have conditional probabilities. All right, now what is next? If you have the conditional probabilities, are you done? Your objective is not to calculate conditional probability of calculating, of exceeding, say, 150. You want to find the unconditional probability. So what do you do next? Once you have reached this point, you have probability of exceeding, say, 100, given that you exceed 30. What else do you need?
Multiply the two conditional probabilities.
Right. Before that, you need to find the unconditional probability using standard Monte Carlo. So you also find the probability to exceed 30, and then you do a multiplication to find the unconditional probability. Okay? And the probability to exceed 30 is easy to calculate because it's high. So if you do simulation, you have a lot of failures. So here is a path with the first 50 states. So we start from 3, we move to this state, we move to this state, and we keep moving. And this is the final state if we have only the first 50. Okay? Now some of the states are repeated states. You may have gone, from example, from here to here and stayed to this point. And this counts as 2 states if this happens. Okay. Same thing for mass ratio and damping. So what we say here is that the sample that we generated is not useful directly because it's conditional. It's only useful for conditional probabilities. So now we calculate the probability of exceeding 30, and I choose to use 40,000 simulations to do that. So this is standard Monte Carlo to find the probability of exceeding 30. So we generate 40,000 values of the frequency ratio beta 1, 40,000 values of the second frequency ratio, 40,000 values of the mass ratio, and 40,000 values of the damping. Okay? And then this is the limit the intermediate limit. Here is, what is this? You probably have seen it before. What is this I? It is a counter or indicator function that tells that is 1 if you have exceeded 30, or 0 if you have not. So you will have here a bunch of 1s and 0s. So if you find the relative frequency of 1s, then you have the probability of exceeding 30. Okay, so here is what we do. We find the mean value of this vector. So here is the probability, 3.1%. 3.1% to exceed 30. And before we continue, we assess the standard deviation. So the standard deviation is about 1% of this. Okay, so we are good. About 1% of the probability failure. These are the confidence limits, 3 and 3.1%. So this confidence limit encloses theoretically the true probability failure that we don't know with 95% probability. So that's good accuracy. So then, as we discussed, we calculate the unconditional probability. So this is the conditional probability theory. This is what do we have here. What is the first term? Well, we look at the Markov chain and we find the proportion of values that exceed this limit. Okay? And this first part is that proportion. And then we multiply this by the probability of exceeding 30. So if we put D equal to 150, we find that the first term is 3.1 by 10 to the minus 3 per 1,000. We multiply it with this probability, and we find the probability to exceed 150. So this is 1 per 10,000 roughly, right? Okay, you can change this value. You can make it, say, 100 to see what is the probability to exceed 100. Okay, this is 1 per 1,000. Okay. So here we have made a plot. We have calculated probabilities of exceedance from 30 up to 200. Okay, so this is a logarithmic plot, and in the end you see that this is almost a horizontal curve. Okay, now here this is about 180 maybe. And then after that, it becomes constant. Why is it constant? Is this theoretically correct? No, it's an artifact, it's the simulation. What happened? Why, if we go beyond this limit, the probability doesn't change? Can you guess? In the beginning, it puzzled me. Yes?
You only have 40,000 samples.
Right, you have 40,000 samples, so after this value, you don't have any up crossings. It doesn't mean that in reality you don't have up crossings, but because we only did, as you said, 40,000, then there are not enough failures above a certain level. Okay? So this is a nice approach that allows you to find probabilities of crossing different levels, and it's more economical than doing a standard Monte Carlo. Okay, this program is on the internet, and I encourage you to download and play with it. You could even change, apply to another problem. All you have to do is to change the equation here for the displacement. If you have a different system, you will replace this equation. But the rest of the method, especially the part that creates the Markov chain, doesn't change. Okay? So it's a good thing to practice with it. We learn an alternative method to sample from difficult, tricky distributions that was called acceptance rejection. But would we have used that method? Yeah, theoretically we would have done that. However, this takes a lot of simulations because it tries to, essentially it's like shooting at random, and if the failure region is very small, then you'll not have many failures. So you will spend a lot of computational time without getting good results. Okay, let me show you some results. I will make a table that shows the results in this example and compares it with standard Monte Carlo. So first let's consider the case that we have only 10,000 states. So when we run the program, we have 40,000 states, but suppose that we have fewer. We have 10,000, and this is going to influence the accuracy. And the replications to calculate the probability of exceeding 30 is 100,000. 100,000. So replications to estimate probability of exceeding 30 is 100,000. Okay. So we'll make a table with a level, the probability of failure, and for level 30, the probability of exceedance is 3.1%. If you consider level 50, then you multiply the conditional probability of exceeding 50, given that you exceeded 30, times this unconditional probability, and you get 9 by 10 to the minus 3. Approximately 1 per 100, okay? So going from 30 to 50 reduces the probability by almost by 3 times. This is 3 times smaller than this probability. Going to 75, the probability is 3 by 10 into the minus 3. It goes down. Going to 100, it is 1 per 1,000. 125, it is 4 per 10,000. And 150 is 9 by 10 into the minus 5. Okay? So this is 1 per 10,000, approximately. Okay, Now, this was done with 100 replications to calculate the probability of failure of 30. Say that you do more, you do 400,000 instead of 100,000. So hopefully you will have more accurate results. So Monte Carlo states still 10,000. The replications to calculate the unconditional probability is 400,000. Okay. So we make this table level and probability of failure 30, 0, 3, 1. Actually, in this case, the results were very, very close, so that I will not repeat it. They are almost identical with this case. So, almost identical. Previous case. And this means that you don't need more accuracy to calculate the error for the probability of exceeding 30. Okay. Now suppose that we do 40,000 states. So Monte Carlo, Markov chain states 40,000. And replications to estimate the probability of exceeding 30 is 100,000. So level and probability of failure. So we have 30, 0.031, 50, 9.3 times 10 to the minus 3. This should be compared to this probability, 75, 3 per 1,000. 100, 1.1 per 1,000, 125, 7.7 per 1,000, and 150. Okay. So the results are pretty close.
For 125, is it going down or up?
Oh, I'm sorry. That's a good point. 10 into the minus 4. So it is practically 4 per 10,000. Okay. Well, in order to compare this method with standard Monte Carlo, let's see what will happen if you use standard Monte Carlo instead of Markov chain. Because you are saying that Markov chain is more effective, but let's see that. Let's investigate that. So, standard Monte Carlo. Standard simulation, and we have 10,000, I'm sorry, 100,000 applications for all levels. Okay, so we'll make the counterpart of this table is level and probability of failure. So if the level is 30, then the probability is 0.31, same as this, because you use no surprises here, because we use standard Monte Carlo to estimate this. For 50, it is 9.2 by 10 into the minus 3. And I'll show you the confidence intervals. 95% confidence intervals are from 8.6 times 10 to the minus 3 to 9.8 times 10 to the minus 3. So this is for 50. The estimates are pretty close. This is 9.2 per thousand, this is 9.3 per thousand, so very close. 75, the probability is 3.3 by 10 into the minus 3, and confidence limits are 3 by 10 into the minus 3. The lower bound and the upper bound is 3.6, 3 by 10 into the minus 3. Okay, here it starts, this estimate starts to deviate from Markov chain. Let's go to 100. For 100 is 1.24 by 10 into the minus 3. And the bounds are 1 by 10 into the minus 3 to 1.5 by 10 into the minus 3. Okay? So it deviates and the bound starts becoming wider. So you have something from 1 to 2,000 to 1.5 per thousand. Let's go to 125. 5.3 by 10 into the minus 4 and 3.9 by 10 into the minus 4, and the upper limit is 6.7 by 10 into the minus 4. Okay? So now for 125, the deviation is not small. Okay? Here we have 3.7 per 10,000. Here we have 5.3 per 10,000. So that's substantial. For 150, we have 1.4 per 10,000. And the bounds are 7 by 10 into the minus 5 and 2 by 10 into the minus 4. Okay? So although the estimates are not far away, you see the bounds are quite high. This lower bound is less than 50% of the upper bound, so the accuracy is not that great. Okay? All right. Any questions? Well, I will ask a question then. Can we use the formula, the standard formula, to find the standard deviations of these estimates? The standard formula is that the standard deviation of the probability of failure is the square root of the probability of failure times the probability of survival divided by the number of samples. Okay? Can we use this formula when we use Markov chain? Now you have to think a little bit. before you answer. This formula is valid in standard Monte Carlo simulation where all the sample values are independent. Every time we do another application, we create an independent number that has nothing to do with the previous numbers. But when we use Markov chain and we create this chain and we jump from one step to another, are they independent? No, they are not independent. So the assumptions upon which this formula is based are not valid, so we cannot use this formula, okay? We have to account for the correlation, and this is a little bit tricky, and I'll cover it in the last, in Thursday's lecture, okay? Any questions? Okay, so let's stop here.